Hey everyone, welcome back to Jetson AI Labs. As always, we're really excited to be with you here today. This month's guest, we have Dr. Jack Silberman from
Everybody wave.
University of from University of California, San Diego, and he's really involved in the race car community for autonomous racing and everything involved in that, and has a whole lot of projects to talk with us about. And as always, we have Jim from JetsonHacks here, along with my colleague Dana. You guys already said hi. Hey. So good to see everybody again. Thanks for joining us. And so before we bring Dr. Jack on, who some of you may already be familiar with because he's like very active in the Jetson community, which has been really great. We just wanted to cover a couple quick news items that have come up in the past month. So just let me bring my screen up here really quick. So the first big thing is GTC season is upon us once again. So generally we run a GPU technology conference in the spring and also in the fall. So this fall session is from November 8th through 11th, and we have all types of free sessions that you can join. Everything about AI and deep learning, computer vision, robotics and autonomous machines to all types of hands-on training. So I encourage you to go check this out here. Here's the URL quickly for you, just nvidia.com/GTC. You can register for this and check out all the sessions that you might want to join. As always, Jensen's keynote is a really big draw, and he has some fabulous announcements every time, along with a bunch of like really high level speakers here from industry and academia. And there's also a bunch of hands-on trainings that I'll let Dana speak to because she's from the Deep Learning Institute.
Yes, Deep Learning Institute is putting on some trainings, and now through October 11th, you can get early bird pricing. We have 7 instructor-led workshops here. These are not self-pay, so you'll have the benefit of the instructor providing help and TAs in the course as you work through the hands-on material. So those are all real good. There's natural language processing course. I believe there's the deep learning course. There's CUDA, there's a number of things, something for everybody.
Yeah, thanks, Dana. These hands-on DLIs are like incredibly valuable if you really want to get down to the nuts and bolts of how you do things. A lot of these are done remotely with TA assistance, and everything is done through Jupyter Labs. And of course, there's ones that you can run on your Jetson as well. Okay, moving right along. Another big news item that we wanted to cover is last week we announced a big partnership with Open Robotics about ROS and ROS 2. So NVIDIA and Open Robotics, or formerly known as OSRF, we've come to an agreement to work together to add additional functionality into ROS and ROS 2 for accelerating GPU performance and adding a bunch of new algorithms and nodes in there. And we have a lot of really good plans to kind of take a lot of the different ROS work that we've been doing and package that into things that are easier to use and containers and all of that great stuff. And there's a couple nodes that are already out. These are on GitHub that you can go check these out. For example, there's a very optimized April tag detector, which is these are like almost like barcode like tags that you would put in like a warehouse or other environment that could aid in a robot localizing yourself. So these are all different ROS nodes that we have, in addition to things like stereo disparity and point cloud generation, and also just general image processing nodes that are all, these are highly accelerated with GPU, and if you're running them on Xavier with the computer vision accelerator engine. And we have a lot of plans in the future to bring more complex gems, we call them. These are like accelerated GPU algorithms, in addition to working with OSRF on improving the infrastructure within ROS and ROS 2 for internode transport using GPU, basically zero copy and low overhead stuff, which we're really, really excited about to work with them on. And we've also done a lot of work on the simulation side. So integrating Isaac Sim, which has support for ray tracing and RTX through Omniverse. So integrating Isaac Sim with ROS and ROS 2 seamlessly, so you can get the benefits of having, fully ray traced photorealistic environment with really great GPU accelerated physics, and have that seamlessly integrate with your ROS2 robots and launch files and all of that great stuff. So I really encourage you guys to check this out. I don't know if I have a link banner made for this. Let me post it in the chat here, though. So this is a really great blog that kind of overviews our roadmap of what's to come. And we plan to make long-term investments in ROS and ROS2. And I personally work on ROS2 quite a lot these days, both making containers for it and doing stuff on JetBot. And it's been really great to work with so far. And I think Jim has dabbled in it a bit as well. Okay, with that, Dr. Jack has a lot of really great topics that he wants to talk about, so we're going to bring him on a while. Let me stop sharing my screen here. All right, there he is.
I'm here.
There, we'll put him up top. Hi, Jack. How are you today? Thank you so much for joining us.
Good. Happy to be here. Actually, it's a pleasure because I learned so much from you and Jim, and I can't wait to put my hands on some of the stuff that Dan is working on. And when I say me, it's the students and the whole community. So happy to be here.
Likewise, Jack. Yeah, and it's been great knowing you. We've known each other for quite some time now, and you've always been a real pleasure to work with. And in addition to all your students, and we appreciate all the contributions that you've made to the community.
My pleasure. So, and we're back here. So let's see if we can share a little bit, right? Because whatever we share today, 6 months from now, people are going to say, oh, yeah, I remember people mentioned this. We're so ahead of it now.
Yeah. So you got a really cool workshop background going on there. Looks like you're into, what scale RC cars do you have there in the back?
Several scales. So I think you can see it on my right side, I guess. It's like a 1/10 and get a 1/8. And then we have a couple 1/5 that we're going to be something like this to all the way to some EV go-kart and to a full scale, like in the autonomous car that probably everybody should be keeping your eyes open for the Indy Autonomous Challenge coming up on October 23rd. Will be spectacular.
So that is like an actual larger car, right? That runs on the Indianapolis Speedway. Is that?
Yes.
Am I gathering that correct?
It's a full-size race car. It's a kind of the category. It's called the Indy Lights. But if you would look at it, it look like it's just a regular race car. Then you're just seeing where does the pilot go in there or the driver, and there is no space for it. It's full of sensors in there.
Okay, and I take it that has some like Jetson or other GPU computer in there with sensors.
Good plug-in. Yeah. So we have a AD-Link computer that's loaded with NVIDIA GPUs in there, and that helped quite a bit on our acceleration of the algorithm that some of those are going to be mentioned today.
Cool. Yeah, and for those of you who don't follow, AD-Link is a partner that makes ruggedized enclosures. So they make both x86 systems and Jetson systems, much like some of the other folks out there. But they're ruggedized, they're IP rated. So if you want to do like a heavy duty type application where there's a lot of shock and vibration, like you might see from an actual race car, then that's the type of system that you would benefit from, as opposed to just taking like a dev kit and strapping it on there.
Exactly. Plus, you have also the power supply, the filtering for the power of it, that make it very convenient for us to integrate, like heat dissipation and all kind of stuff. It's a pretty nice machine.
Cool. So tell us a little bit, Jack, about the courses that you teach at UC San Diego and the activities that you do with your students there to get them into robotics and teach them about autonomous systems and things like that.
Yeah, primarily I have 2 classes. One is focused on engineering students. It's a mix between mechanical engineer, electrical engineer, but actually any student can apply for it. I had a couple people with business background now, and someone with market background, and some of the students were looking at each other, what are they doing here? And saying, it's awesome. You know, you have to sell something one day, let them learn with them, and then we work together. So we break them in groups, and incrementally we have challenge, right? Number one, they just receive a plain chassis RC car, and within a box full of components, literally box full of components, and then some instruction. Some of the others is really look for the data sheets and knowing how the parts get together. And then I'm lucky enough to have 2 tutors/TAs that go around and give them some hands-on experience for people may not have. And then everyone start with a simulation, and there'll be an interesting discussion later when we get to talk about simulation. But we start the simulation because usually the mechanical engineer trying to gravitate to the mechanical aspect of the design, they let people waiting. Hey, Justin, you're a mechanical engineer. I'm going to start my work when you finish yours. Jim, and then a software, and then they're waiting for the mechanical, the electrical, and the software to work on it. And we don't have time to keep waiting for this, right? So we have to make sure that everybody has a chance to do their work, and then we integrate. So we start with a simulation, and then it's exactly the same software that we run on the hardware. For example, we have the Jetson that's run on a hardware, but also run that in a simulation. We have the Donkey Car AI framework and the F110 that's primarily ROS2. And then we teach them, and everybody has to go through some of the experience of software development before they put their hands in hardware. But on the very first day, they receive the box, they start to design. Usually take between 2 weeks or 3 weeks for the robot to be completed. The first team that finish that robot get a free boba drink. Boba drink go a long way with students. It's just they go excited about it. So then the first team had the bragging right to say, hey, we finished. Finish means it worked. There is an emergency switch that worked. All the basic capability that is not autonomous yet, but you could, for example, do a drive-by-wire. And then after that, they go through deep learning primarily as a black box. I usually get to the class and I flip it. I show it working so people get excited versus being another 3 or 4 weeks of the neural network, as artificial neural network theory, and then you plug it in, and then you see it working. Now we see it working, and then people say, "Aha, my God, this works." I'd like to see actually how it works better. Then become a gray box, and then become a white box, and then we introduce ROS, computer vision, and then at the end they have to have a final project. And I have a little video that shows some of the final project people are working on that they decide, and it's open as long as they didn't repeat 100% of someone learned in the previous quarter, and they have a budget of $100. So each team has $100 to add to the robot. But let's say Jim's team, that's team number 2, and then it's team number 3, they just use $30 each. So I have $70 from here and $70 from there. I have $140 plus my 100 jacket. I have $240. Can we buy this RGB D camera, like 3D camera? Say, yeah, it's within your budget, and then we go buy. So we have a little budget that every quarter we go over it. Yeah, so if I may, I can play this little video. It's a good summary of what actually we do on the class. This is a group 6 from just after the pandemic, start to get back together, and then you're going to have an overview of what they do. So this is, for example, it's ROS running on one of the robots that they built. So this is probably week 6 after we did already the simulation and building the robots. And then now you're just demonstrators. So each of those have to demonstrate indoor and outdoor labs, and some of the
that's cool.
members.
Yeah, I've not seen many instructors or people like really put an emphasis on outdoor as well.
Yeah,
These RC cars.
It's funny. It's funny you mentioned this because actually my PhD is in field robotics. So I have done so many things in the lab, and I want to go outside, and you know how things goes, right? The weather, the lighting, the wind, the traction, the kinematic of the machine. That's attracted me a lot. So this is an example for one of the computer-based training that we use, some of the simulation. Then this is actually people running a competition online. Basically, we have some NVIDIA GPU, and then that's allow people from all around the world to actually come compete. So my class, all the students go compete on a monthly basis with other people.
So they're competing in simulation here then, right?
They were, yeah. In this case here, so everybody could be anywhere around the world, and then I have a server on my home office, and then it's basically think about like a multiplayer video game.
So they're each individually going around the track, and then you're comparing some kind of statistics or how they did to decide the winner.
Yeah, so basically you have the timing. So let me get back. So each of those, for example, this is a real time, and they have the screen, and we have a lap counter, and then each of those has the time, and then later on we select the top 8 to go to the finals. But yeah, so they compete individually. That's the whole point of like now you can't be, hey, I'm a mechanical software person, or mechanical person, not going to be doing software. Well, you have to do in the beginning, right? Because we all know that we have to work together in teams and we have to communicate out of school. And if you just know mechanical engineering, if you just know electrical, and you're just a software, you won't be able to be an effective team player. So we give a chance to everybody to be able to contribute a little bit, and then later on you can just specialize. So this is actually was before the other video where they received just the chassis. They have to develop from the ground up. They just received the parts. Again, look at that, another outside track. And then they have to do 3 autonomous laps. Again, the boba come together. So this is what in quote indoors. This is lucky enough to have several resources at the University of California, San Diego. We have 2 or 3 tracks around. This is an outside classroom.
Nice track.
Yeah,
so is that using behavior cloning? I've seen that a couple times in your
it
video.
It is using a behavior clone. This is a track, actually, if you think about it. This is when we had our pandemic hit, and then for 1 quarter couldn't teach, but the very next quarter this tents were up, and then faculties that wanted to teach in person were allowed to teach in person. So that's still considered outside, inside environment hybrid, and then we have to follow the usually the precaution for COVID-19. But yeah,
that's an awesome track.
It. And then this is the other outside track that we have. And as you can see, some shade, some sun, and that change, that add a whole other level of difficulties and challenge for the students. Yeah.
Plus the track itself is physically, it's going to feel different, right? To the wheels, the traction.
It does. Good question. So as you can imagine, the traction here is completely different that we have on artificial turf, right? And then the students have to do and learn to do that.
And how'd that work out?
Depends. In the beginning, they have that all lesson learned. So yeah, what we have done here, and we could come really quick, and now we're slipping or we're tipping over, and then that's actually that's a good lesson learned, right? But you work on a simulation, don't necessarily work on the real world, and then you keep tuning it and keep understanding. You go from that learning experience and improving every time you go through.
So when you make it work better, do you gather data from outside and then just train it for whatever's outside, or do you do some other method to try to make it generalize?
Yeah, so good question. So there is 2 parts of it. One is that what my camera is seeing, what's the environment look like, and then how can I generalize that? And we can make people stand, right? Because you just have this virtual environment. You can make the light conditions change, and then that way you can deal with that. But if you think about that, like just to take a look on the reason I was showing this, I don't know how well we can see, is look at how much of the light conditions, even us have a hard time seeing the lines, and on purpose put the different colors to try to make sure that the students learn how to do computer vision with different filtering. And then you can't think about all the conditions all the time. And that's after we learn, after each of the competition, we have some learn experiences that we share, and then we go back to people that develop the simulation and provide them feedback.
So you mentioned computer vision and the lines and behavior cloning. What type of algorithms or DNNs do you typically cover in your course, or the students go off and implement to actually create the autonomous behavior?
Yeah, great question. So in the beginning, as I mentioned, we give this almost like a black box where we have some convolutional neural network that's pretty shallow. So it's kind of sensitive for change on the background, for example, and then for addressing the question. So if you train for all the different conditions they're going to see, then you have a pretty robust model. But who has the time to think about all the different conditions, right? So one of the things that we're experimenting is that can we share some of this model? Someone collect a model, and then you build it, and then can you share with some other teams? And we're still trying to experiment that with the amount of data that we have. If we have GPU acceleration, the timings reducing significantly, right? If you do some training just on a CPU, maybe it take you 2 hours to 3 hours. On our GPU cluster that we have access that we said it's about a minute. So we can do much more training than doing that on a regular CPU. So the algorithm in the beginning, it's a black box. This basically convolutional neural network. Then we do regular traditional computer vision with OpenCV, PID control, for example, what this we see now on the screen in terms of following a target is primarily traditional programming. And then the students then can go and modify. For example, on the Jet Racer framework that we use on NVIDIA, it's a completely different architecture from the donkey car. and then I can just give you some of the information. If you're interested in getting into this, it's relatively easy, couple $100. You can start with a robot of this size, and some of the components inside you can see it has a NVIDIA Jetson Nano. Easy to get in, couple $100 to some more sophisticated robots that have a LiDAR that would be just LiDAR itself, could be $2,000, but you can get small LiDARs now for $100 that will fit on there.
Yeah.
So it's relatively easy to get in.
Show us that thing again, Jack. Sorry, I had you small.
Yeah, so this is a, if not mistaken, 1/16 scale. So pretty compact, easy. Jetson Nano, little fan on the top just because we want to keep things cool, not required, but since the electrical engineers and mechanical engineers have to work on some improvement, that was some improvements in the 3D printed camera mount. A camera, basically this is our primary sensor. Then the output, you have a PWM generated pulses just because Linux is not deterministic. Then you have something that can generate some, like the PWM, pretty precise way. And that's about it.
Yeah.
Off the shelf RC car. So
pretty
this
neat,
is
compact design.
Yeah,
there.
this is, think about like a hello world from AI. You can do this for a couple $100. Now, when you get to the let's say of more sophisticated and or the competition level of university, then you may get a robot that's a little bit more sophisticated, and we use that when we go, and it's basically based on the MIT car F110 from UPenn and other universities, where you have a LiDAR on front, this RGB camera. We have a Jetson Xavier NX, significantly more powerful than the Jetson Nano, and this can do everything that we have thrown it at this point. It's like from mixing neural nets to traditional computer vision, TensorFlow acceleration. So it's pretty nice machine. Significantly more expensive. A LiDAR this type is probably just LiDAR itself is $2,000. You can see outdoors, you can see 20 meters out, you can have a high refresh rate and less expensive. But for the proof of principle, you don't need this. And you can learn quite a bit with a less expensive piece of hardware. But this is our, they call it college level competitions. That means someone has to sponsor you to get to one of these, unless you have some money that you put it in. But that helps us to do quite a bit of development.
Does it basically boil down to like the sensor package and more expensive sensors and computer board?
Just think about it. The faster you go, the more you pay attention when you're driving, right? You have to be tuned, you have to see farther. And then if you can close that loop fast enough, then when you see things probably already happened in the past, because when you have enough time to process it, you already passed, and you may not have enough time to react. So depending on what you're running. But for the principle, the more you fuse the sensor, the more reliable, not single sensor going to give everything that you need. We all hear about the computer vision versus the LiDAR from some of the industries of cars that we see on the street now. People say I don't need a LiDAR. Some others say if you don't have a LiDAR, you don't see the things that you don't see, right? And that's a discussion.
What's your impression of that? Because obviously your students in like the 101 level or whatever 200 level, it's only a camera, but it's a simpler course driving slower. And the more advanced one that drives faster does have LiDAR. And what do you see the pros and cons of there?
So it's different because for one of the classes, they have to build the robot from ground up. So we focus just not on the software that's going there, but the sensor, but building the platform. So when they come to the point that they're going to be developing software, if you start to throw in more sensors, then they get to diffuse and they can't go deep in anywhere. So we heavily depend on computer vision. Now, on their final project, that could be 2-3 weeks. If they want to add a LiDAR, then they add a LiDAR and they have to run with that. So my opinion is that depending on the kind of problem you're trying to solve, right? You have to see edges very well, and you want to see something that doesn't necessarily require a 3D. 2D will be okay. Then a LiDAR can get you a lot, right? You have features, walls around. Computer vision, if you can deal with different kind of light conditions, solve the problem. So basically give you the building blocks that when the students want to go run more complex algorithm, they have the fundamentals, right? To the point that you think you know something until you know that you don't know enough, right? but you get them enough to think that they know something, and then to start to discover more and get in depth of things that they haven't studied yet. Enough to be dangerous. Let's put it this way.
So there was a question from the chat here. They were asking, is the bigger vehicle, I'm assuming like the MIT F-110 one, they said, is that available for sale as a chassis or kit?
Yeah, so the question would be yes, and I couldn't think of anybody better than Jim to answer this question. Jim,
yeah, so there happens to be a store. If you go to racecarj.com, you can buy most of the parts for, so there's several versions of the car. This is for like the 1/10 scale, the bigger cars. And they come in 3 versions. One version is, they're all based on this chassis that Jack's showing. One is in an MIT configuration, one is in an F-110 configuration, and one is kind of for a hobby experiment type of version. So if you wander over there, take a look at it, kind of get a feel for some of the different flavors. And they all come in.
There was a question from the chat, is that using a Traxxas
right,
chassis?
Traxxas Slash, which is probably the most popular 1/10 scale.
And let me add to that. And I think it was a great pick of a platform, because my very first class, I tried to get something that was light, beautiful, carbon fiber chassis until we start to have to buy replacement parts. And then as soon as I contact the vendor and say, okay, how many boxes do you want? I said, no, I want 5 parts. I said, no, I send you boxes of parts. So when you get one of those chassis that people actually, it's pretty common on the has the hobby community, you can buy everything you can imagine of replacement parts. It may be a little bit more expensive in the beginning, but on the long term, I can guarantee you it's worth it, because I was in some competition that someone broke a part. You just literally run to a hobby shop, come back, and fix it. So as Jim was saying, that's a pretty proven platform on the RC world, and you probably can buy all the imaginable parts that you can. That's right. Think about like a Toyota and a Honda. You can buy on the corner some of the parts.
It has all the hop-up parts, and because they're off-road types of vehicles, I mean, the first thing people do when they get them in the RC world is they try to jump them as high as they can. And the vehicles out of the box go about 50 to 60 miles an hour. So they'll just throw them off a ramp, and they'll go about 30 feet in the air and come down, but they don't break. So that's
those are real shocks there, Jim, right? They have oil inside. It's not your toy that you have just a spring that pretend to be a shock. Those are real shocks, oil filled. You can change the density of the oil that you have in there. And that's the good and the not as good. You can spend so much money upgrading those. You can see that the Jim has this really beef up coils already in there, because probably start to get heavy, and the most likely the chassis was bottom out, and you can see he already put some very nice shocks in there.
Right, and kind of this is the experimental model. So I just have a Jetson Nano on here, and then this is a LD LiDAR. It's very small. It's a $120 LiDAR. And then this is just a webcam. So you can put all different sensor suites. I think one of the questions was, so why do you use expensive sensors? And one way to look at it is, if you have a sensor like this that can see 10 meters, that means that you can see like 1 second ahead of you if you're going 20 miles an hour. And if you're going 40 miles an hour, which these cars can well within their capabilities, that means you have a half a second, you can see a half a second ahead. So that's why you spend up not only the amount of time that you could see ahead of you, but also the actual density of the cloud in front of you. So on an inexpensive LiDAR like this, you get maybe 5,000 samples a second, where on the more expensive LiDARs, you get 45,000.
And that's a great point for answer, Dana. Like, can you test some of the different things in a simulator. Yes, if you go back and put that LiDAR that Jim just showed to be realistic and another LiDAR to be realistic, that the student to do experiment this, but hardly people going to do this. You just put a generic and then say, look, it's a perfect world. My LiDAR can see 100 meters out. And then you get one of those LiDAR that Jim has and say, well, not quite that, right? It's 10 meters on a good day, perfect light conditions versus the sun hitting you or not. So those things are hard to simulate. You can spend the time and you can do it. It's just like who has the time and the resources to do it.
Well, I think that's one of the the last 5 years we've seen such an advance in simulation technology, the physics engines, the graphics. It's absolutely stunning how much has changed, and then you realize how far away you are from actually simulating real when you go from sim to real.
Well, and then when you do simulate this LiDAR or that LiDAR, there's always going to be a new one on the market that then you have to create its characteristics and simulate a new one.
Absolutely. Absolutely. There is a famous, like I said, partner to ROS2 and to some of the AI framework that's the SVL simulator, pretty realistic. And one of the biggest problems they have now is that what chassis or kinematic do I have to support? Who's going to do it? They have the building blocks, but someone have to go there and they're going to do this chassis. They're going to do the other chassis. They're going to do this specific sensor. And then, of course, everybody wants these things ready for them, but who has really the resource to develop every single sensor, to your point, Dan? And so then you can do something that's generic enough we put to learn, and then we go to the real world, then you have to adapt. And you have to tune. But like I think it's awesome. Yeah.
It's like 3D modeling. Everybody says, well, I can just 3D model stuff. But that takes a lot of time, and it's quite the investment to actually build things like that. There's a lot of knowledge you have to have. One of the things that struck me, they just had IROS 2021, which was a Formula 1/10 competition in Prague. I think it was yesterday. And you could tell the simulations of the track, what they were expecting, and then when they actually got on the track was slippery, so you could see that the cars weren't handling that very well. But to model the friction of the floor or the carpet or whatever you're racing on.
Yeah, it's fun to mention this. I can share an experience with you where a week before the competition, we thought we were pretty fast, really good. We have a carpet in a room at UC San Diego, and then we went for this competition in Northern California, and then of course the carpet was different, right? And then the cars were tipping over, and then so how did it come? Oh yeah, the friction for the carpet is so different. It's grabbing much more. Hey, quick question. I have someone doing some yard work outside. Can you hear the noise? Should I mute?
You're fine. Don't worry about it. I have a dog here. We're good.
I assumed it was race cars and that you were
no, but he's just outside, and I can go back and say, "Hey, give me some time," but they won't. So
sorry, go ahead, Dina.
No, I was just thinking about this simulation with the friction and everything. I mean, can you create some kind of range of frictions that you could try and train to?
Yeah, absolutely. Yeah, and then we do. Right. So the question now is, let's use Jim's example. How do you know was the friction on that particular track if people don't go there and find a tool that they can even measure that? You could say the carpet. Well, there are several carpets. Then I remember one competition that F1 team had was somewhere in Portugal with this beautiful colonial building. It looked like just ceramic. Well, whoever thought about racing this rubber tires on a ceramic floor, I'm pretty sure traction was a problem there. So then the answer would be yes, we can, as long as we know what it is. And then who actually ever measure this specific tire on that specific ceramic? Nobody.
So I was just thinking, if you train at different things, you'd still have to have some kind of feedback from the wheels that were telling you what it was finding.
Yeah.
You would need to have some other kind of sensor.
Yeah, awesome question. So that's one of the things that people then now do on the scale is that, hey, can I do traction control? So then if I add, let's say, an encoder on each wheel, and I know that I'm assuming you go straight and the wheels is slippery, well, the only thing could be changing there is really the traction is different, right? Where I put my power, then something slippery, or we go on a curve. and assuming I have the kinematic for the wheels and I know what the angle look like, and they are not really spinning on the speed that I thought, it could be slippery. Or you have a sensor that's an IMU, you're trying to find out if you have some dragging and things there, and then you can compute. So you can, and this is awesome project to do on a much less expensive than do on a full-size car. I love it. It's like so affordable. And if I just tell you what's coming after this, is that I actually do have something on my screen that basically show you that we're not even talking about underwater and above water yet, but I'm just in terms of the, if I show you some of the pictures, I don't know if you can see this already. Well, then what do you go after $200 and a couple $1,000 RC car? Well, how about a go-kart? So a trust, was about a few weeks ago at Purdue University. It's a brand new category of autonomous vehicle. It's, as you can see, it's a real go-kart. So this is a racing go-kart used for high school.
Can you zoom in on that a little bit?
Yeah, I can. Better?
Yeah. So it's basically like a go-kart.
It is a go-kart. In fact, you cannot modify the driving mechanism. So everybody has to go exactly the same tires, motor, because it's not about necessarily who has more money, but they're trying to leverage. This will be the go-kart that the high school team would race on the same race track. This is a track at Purdue University. And then you go build stuff on the top of it, right? So the secret juice here would be really your sensing capability, your software, your computer system, right? So this was the very first time we participated. Actually, it was the very first time that any autonomous robot was able to make the track. You may think that is relatively easy. It is if you put the time, but in a pandemic, 2 years almost, nobody had time really to do much development. So the reason I mentioned this is now you can take a little bit more of payload. The kinematics, it's a little bit different than what you have on this RC cars, because you can see it's tires, mass, asphalt. It's a little bit closer to the real world. In fact, we did use this go-kart, or we're planning to use the same sensing, the sensor suite that we have on the big race car. So there is some places that you actually remove. We have a Jeep that's a pace car. We've removed from there, put it here, LiDARs, camera, and then radars. And we pretend to be the race car because it's expensive to take the full-size race car on the track. And then you're trying to, because the cameras and the sensors are about the same position, we're trying to collect data and go from there. So this is all on the plan. So we quite haven't got there yet, but this go-kart is ready to help us do this. So the reason I mentioned this is because it's much more affordable than a full-size car. I think this chassis itself is a couple $1,000, some of the electronics another $1,000. So let's put this way, for $6,000-7,000, you can build something like this without your perception system.
But it's basically a car. And I'm curious, how does the software suite on these larger cars differ from the smaller 1/10, 1/15 scale cars? Like, do these also run ROS or ROS2 and DNNs?
Yep. And to be honest, does not change much. We could do exactly the same framework that we have. It's just because you can carry more computer power, and therefore you could add more sensor. For example, we have actually 2 LiDAR that's solid state that points to the left, to the right, versus this one that's, and it's they're 3D LiDARs, for example, and the IMU and the cameras, and we could fuse all that just because they have a lot of computer power on the back versus on the scale. As of today, until you guys figure out how to do pack more on 10, 15 watts on computer, that I'm pretty sure going to come in another year, we cannot do that at this point for this for the resolution that we're looking for.
So, and you mentioned this sharing a common payload with the larger IndyCar that you're doing. So does this one also have like the ruggedized GPU system on it, or what do you use for compute on this thing?
It does. It's actually on the back, we have an AD-Link computer, and I'm not plugging in here. They actually sponsor us. And then we have an AD-Link computer that basically has an just basically an Intel CPU, And then inside, you have this regularized computer that you also have the NVIDIA GPU in there, if I'm not mistaken, 3090. And then that has, I don't know, 3,000 CUDA core, if I'm not mistaken, or more. And that helped us quite a bit. We can accelerate
Sure
a lot
did.
of stuff in there. Yeah.
Yeah.
Now, how to power all this? Lots of batteries, right? You have this box here, and the other box have the battery. And actually, that help us because the kinematic for a go-kart, when it's developed, is of someone to be sitting here. And then if you remove the human, then that means the friction of the tires, everything change. And then instead of putting weight, we just put more batteries, and then now we have more juice.
So is the thing still gas powered though?
It is not. It's actually a whole other category. It's all EV. I should have told this. An EV
Oh,
Grand
right.
Prix is a brand new category, even though it's in Indianapolis, the capital race of the world, and people like the noise and like the things. But this is a brand new category that's an EV Grand Prix.
EV car. Okay.
And this is actually the bottom part actually was developed on Universal Hawaii. Our cart was delayed for several months, similar to the problem that Jim says in terms of parts coming, being shipped. So this, we got delayed about 2.5 months. So Universal Hawaii had some of this parts. So they unplugged this from their cart in Hawaii. They sent this to Indianapolis. I sent 2 students that spent there about 3 or 4 weeks putting together. And then the reason there is a seat and the steering wheel here is just because this is a dual use. If a human sits in here, she or he can drive it. And for example, can collect data. And of course, there is a whole safety aspect of it. But if someone presses the gas, in this case, it will be a throttle and the brake, it automatically activates the EMO, and then the human take control of the cart. We are working on another generation. There is no seat and there is no steering for obvious reasons. I don't want the students going on the UCSD campus and driving around and get in trouble. We just remove their primary to protect the humans.
Awesome. So I have a question that kind of harks back to what you guys were talking about with like the motocross style RC car tracks, which is like what a lot of people do when they're actually manually driving them. So in like the infancy of these autonomous RC cars, it was mostly time trial mode, right? There's one car on the track at a time, and you're basically just seeing who can go around the fastest.
Right.
I've started to see a little more Grand Prix style where there might be 2 or more cars racing simultaneously.
Yeah.
I was wondering, like, what do you do? Are you still mostly time trial or?
So depends on the simulators. We are definitely putting 4 cars racing at the same time. When you do the real world, and I don't think I have a picture here in Northern California, that's the do-yourself robocars. We do 2 per time. At this competition, we're supposed to have 2 at a time, but nobody proved that we were safe enough, so we didn't. But next year, we expect to have multiple agents. So we call it multiple agents.
Kind of expensive you have a $6,000 go-kart and they crash into each other.
Yeah, and imagine now $1 million cars. That's the IC kind of development for those robots. So in theory, you're going to have multiple agents. Right now, as we speak, this week, you have to prove that you can see a box in front of you that simulates another race car. You have to detect them. Detecting a car that's primarily built out of carbon fiber is not trivial, right? Some LiDARs may not see it very well. Some radars may not see it very well. You may be having reflection of the other sensors from the other cars. We're trying to work on all this, right? And I'm a level away. If I have 2 students living there in Indianapolis, working with the University of Hawaii, California, and working with Gaia, building our race car. And to answer your question, how about that in process, independent of what you're doing? The RC car is much more affordable, so we race all the time at UCSD in our track, multiple cars. Here, I can put multiple cars. Usually we have 4 of those going, but they rarely break, as Jim was saying. If they break, they're affordable. This is
So does
more
that
expensive.
require explicit collision detection and avoidance software, or is it just like baked into the behavioral cloning that they do?
Yeah.
Or
So the answer would be both. right? If you're doing a behavior cloning and you're trained to recognize another car and go around, and I think I had a video that was showing go around cones. We basically just put the cones around the track. And I forgot to tell you, also put aleatory cone that we have to go around. And my next challenge will be to have a pace car. So we have the two cars plus a pace car that keep changing left lane to the right lane every few seconds, and you have to go around and not crash. So depending what you're doing, right, with behavior cloning, so you have to get something very close to what you're trying to do, such as we give an advance to the pace car, and you train pass every time you go around that car. The other thing is, if you're going to then program it, then you have to do a bounding box around something that doesn't look like a track, and then find is on the left side, is on the right side. If I'm going to pass from the left side, when I'm going to get out of the track, and if I get out of the track, am I going to lose that lap because now I go around the cone on the wrong side, or I should wait for the next moment that I can pass. It's very similar to some of the rules for racing.
Yeah. And how do you like reconcile or integrate more of like the end-to-end networks like behavior cloning, which essentially
Yeah,
take in an image and output like throttle and steering controls? How do you integrate that with more like discrete logic that might come from vision-based DNNs or computer vision, like the bounding box type?
yeah, awesome question, right? Some tools are very good to do something such as recognition of an object that I already show it in advance. So then let's say I can use some neural networks like face recognition. When I go to the airport, I travel quite a bit. I used to put my passport, now I just show my face and you know who I am, know they have a clearance, go through, right? So we do, and we don't have this now, but we are working to have it. Some of the final projects for the team is exactly like this. How can I get the best for both worlds? And then I can tell for some of the hardware we have access now that can do some tensor acceleration. And then that gets so much nicer. And even the smart cameras, right? You have some of these OKD cameras from Lusonics that the code actually run on the camera. Then I don't have to be using even my CPU's less GPU time. You just load that on the camera and it can recognize the things that you're not supposed to be doing there to a certain extent, get to the distance, and then you feed that on your global planner. Right, so we have this global planner, I have to go around the track. Then the local planner is where I am, is there something in front of me, should I go around it, right? And that the little camera that has already his own acceleration on it help quite a bit also. So there are so many things happen, as Dan was saying, every 6 months, right? And that's why I don't have a book. It's a no book, it's all basically online, and we have to be every time changing my curriculum. Sometime I have to change on that week. Right now for this new 2 classes, I have to prepare this week and what I'm going to be teaching next week because it changed quite a bit.
Awesome. So I know you do have some other topics you'd like to discuss, like RoboSub and stuff, but I do have one final question for you about the race car stuff. How long do you think it'll be before an autonomous race car would be on par or exceed the abilities of like a human driver?
So in what scale are you talking about? 1/10? I can tell you that now we drive faster than the humans that we bring to compete. So once in a while, we bring a human, and when I say human, it's someone that's relatively good on the hobby, and then they will always faster than us. Now I can tell that there are 2 particular competitors that's on the OnLink, Andy and George. I mean, I don't think anybody can drive a RC car as fast as they can do because they primarily have every single point already in different conditions already pre-programmed and going to do again the same way, unless of course there is a cone, there is a car in front of it. So on the scale, I can tell you that we in Northern California, on this 1/10 scale, we do as good as human, if not better. And I'm gonna say human, you and me cannot drive those RC car faster than the robots are doing. If you get a pro driver, I'm curious about it. But someone that's at a hobby level, we bring it them all the time and we do faster.
And then what about the larger race cars, do you
Yeah.
feel?
After October, let you know.
Yeah. Obviously that's like much heavier duty and much more professional, but
Yeah.
that's still super impressive because I remember when we started with these RC cars, like the Jet Racers and the MIT cars a few years ago, like we would limit it to like 20 miles an hour or something more reasonable. And it's like done in your basements, and the scale of the tracks have just gotten bigger and bigger and bigger, and people are driving faster. And it's just been awesome to see it progress over time.
Yeah, so excellent point, right? So let's say this robot take crash, and if you don't break this LiDAR, that's probably $2,000, and everything else for $30, $40 you replace, right? Now you go on a race car that most of it, everything is out of carbon fiber, and we're talking about dozens of $1,000s to fix, right? And I can tell we crash quite a bit, and then we fix quite a bit, and now we crash less. But every time we push the envelope, right, I can see the car dragging already on and sliding on carpet. And there is a whole other category of RC cars that's on the dirt. And then if you think about it, and I don't know if it's Virginia Tech or Georgia Tech, that's pretty impressive to be able to go and you keep drifting sideways and you're controlling that, and it look like a human, and it's not a human piloting it. So I'm indirectly involved with the full-size car just because my budget doesn't allow that. I'm an associate team. University of Hawaii has all the credit for actually raising the money and having a real race car. I can even show a picture how to look like. The graphics now, it's beautiful. It's like awesome. And then we are every week getting a little bit better, right? So I don't want to tell you much of the speed, but it's not 60 miles an hour anymore, right? And then you and I probably drive that at 60 miles and 80 on a racetrack, and you already start to be scared of it. And then the robots are doing that already. Now, can we get to 180 or more? Then it will be a whole other challenge, right? And then think about it. This is not being around for several years, like this scale, right? As you mentioned, Dustin, I know you for several years, and we're getting better and better, right? Like Jetson was a game changer for us, right? In terms of how much computer power can get on a 5 watts to 10 watts. Jetson NX, my favorite platform. I still haven't found the limit for it yet. And then I can easily run Jetson AGX on that go-kart and still have computer power left, right? So we're thinking about tomorrow using that to do all the things that the main computer is not looking at, such as there are cart in front of us, also a race line, and using that in terms of reverse mention, right? Can we get some neural net to predict things far away that maybe I'm not seeing necessarily with the LiDAR, and I see with the camera. And then just like when we drive, I can see far, can I see in the middle, and can I see it close, and then maybe dedicate some computer powers to do that. And I would love to do that, right? And then with an $800 computer to do that, it's like awesome.
Do you have a picture of the Indy Light car?
I do, and I have to give me a little minute because I have to dig that from my email. So if you stop sharing my screen, and then I'll look for that, and I'll be back. In the meantime, maybe I can give you some of these other things. How about those things on a boat? This is above water, right? This is a whole autonomous boat. There is a competition in Sydney, Australia in November of next year. And I work with a team, believe it or not, from high school students. We will award boat like this. If I'm not mistaken, just the platform is $75,000 without any of the electronics on the top of that. So we have a high school working with University of California, and I'm going to be building a robot that's above water. And if you think that's challenge, how about something? Where is my switch?
So what type of tasks do the surface boats normally do? Is it just navigation or looking for?
So several tasks. In the beginning, you actually don't know. You have to decode something using computer vision. And once you decode, then that tells you some of the tasks that you have to do it. But you have to go for gate, and similar to the underwater robotics also. The first thing you have to go for gate. And you may think it's relatively simple. You put some current in there, and you move sideways, and you have to correct for that. Then you have to use some specialized camera that's maybe in spectral vision or not, and detect some other things. You have to hit some targets. You have to do some parking. So there are several, I guess, missions that get associated with these boats. Right now, our boat is actually doing the Scripps Institute of Oceanography. You want to do a dual use. You want to use the boat, of course, to learn robotics and the robotic competition, but you want to do science. So our boat is going to be retrofitted with several sensors that then scan the base around here, San Diego, to do real science. Since we have the asset, why not use that besides just the robotics competition itself? we learn by having to control that. We learn by doing the science, and then everything that we do will help us actually compete next year.
Where are these running? Where it looks sort of like an ocean or a...
Yeah. So I don't know what this was particularly. This is first year going to be involved. I know we're going to be in Australia. So here's an example. There's to answer your question. So it's a bay. We're going to be. I was in Sydney a couple years ago, and then you see the beautiful picture of Sydney. We have that opera house there, if not mistaken, is the name. Pardon me if someone from Australia, I think I'm saying this incorrectly, but it'll be around that bay. So you can see it's not quite open water, but with those boats are capable to do open water. And I think this maybe was a calm day, but you can see some of the stuff that we're going to have to do it. So those boats are fully loaded with sensors. You can see some of the typical EMO switch. I don't know if someone's going to go swim there and hit it, but if you get close to somebody, probably can hit it. What else? Here we go. So that's the answer in some of the things that's going. Here's a simulation, of course. That's how people are going to be, and see some of the targets. So we would have to go read exactly the missions will look like, and I'll be able to talk to you a little bit more. And this is pretty challenging because on the top of that, there'll be a drone that has to take off out of the platform, scout, tell you what's the best path, think about your global planner, transmit the information back to the boat, and then the boat, we're going to have them to do this mission based on the information that the drone gave. And the drone may or may not come here to land back, but we're shooting that they're going to go land back here on the platform so we don't lose time flying the drone back to land. Guess what platform we, in terms of computer power, so we have 2 AGX that we're going to be using to do the whole computation. We think we can do that on the AGX, the Jetson Xavier AGX, and it should be powerful enough to do this stuff. Now, I know, Jim, that I have to get that picture for you, but I cannot pass this. This is pretty cool. That's
yeah, that's okay. We only have a few minutes left. So.
Yeah, don't worry about the picture.
So this is another thing that we are involved. It's underwater robotics competition. Turned out to be right here in San Diego. This is a simulation. It's live. Anybody from the world could create a model and then spin your robot underwater, because not everyone can come to San Diego to practice. In fact, we can go to the Navy facilities here and train, right? If not, we have a competitive advantage. So we developed this simulator that's open source. And of course, this is the model for on sub, but the targets, everything is as realistic as we have, right? You can see this white tents here on the top. That's exactly how you will see that on the pool. Color the water as best as we can. I guess one of the questions from then, how realistic it is. This is our first shot, right? Our cameras.
Oh, is this from Team Inspiration, Jack?
It is, yeah.
Okay, so we had these guys on a couple episodes again, and yeah, I forgot to point out that you are one of their advisors, and they're just an amazing group of kids. What they're working on.
This was all developed for high school students, right? Actually, one of the main developed for this is a high school. Now he's at college, just got to college in France. So we work together with this. But you can see very far with cameras. Someone asking, is all computer vision? Not necessarily. Underwater, you can't see really far. Then you have to do a lot of natural navigation and get close, and then the cameras kick in. There are sonars, there are other sensors that we use.
Man, you must be just like a busy guy. And I don't think we pointed out, like, you have a day job as well in like a biomedical company.
I do. I work for probably one of the best diabetes care company in the world, and I'm not shy about talking about this, right? We develop sensors that go on the arm of folks and they measure glucose, so you don't minimize or actually don't have to prick your finger anymore. And I can tell you we are number one company in the world now in terms of volume of sensors all around the world. So we're pretty happy when people tell us, hey, thank you, and you changed the life of my kids or my family, and make you feel good about it. Yeah, that's my day job. So everything I talk so far here is my after 5 o'clock job. 5 p.m.
Yeah, I'm sure that's just a great feeling, and it's just so awesome that you share all your experience and share that with all the students and create the next generation of roboticists out there.
This has been really interesting. Thank you for coming.
Yeah,
You're very
great,
welcome.
Jim.
Anytime. So I believe Justin already shared all the links. It's this open source, the code, the design. You just take a look at what some other teams have done, and then you can just basically go what team one have done, the project, and everything else. So it's all here. It's all open source. Here's an example why Jim put that beta shocks after you load this robot, see how low it is. That's why Jim is smart the way that he is. Put beta shocks already on this robot.
Yeah, well, it's funny. You take a car that weighs maybe 3 pounds and you put another 5 pounds worth of sensors and stuff on it. It gets droopy drawers.
It is. So, yeah.
All right. Thank you so much, Jack. This was just
That was
a real
great, Jack.
honor having you on this show, and yeah, we really look forward to continuing working with you in the future.
Maybe another follow-up. You ask me how fast race cars are going compared to humans.
We can.
And then
We can have you again on in the future for sure.
We'll see.
Yeah.
Even
next year.
We go maybe on the go-kart and we get a lot of advance because that we have much more leverage on that. And then we talk about the race cars because I think we're far away. Like think about those professional race drivers. It's like awesome, right?
So when's your next competition?
So we have one in Northern California coming out in October. Unfortunately, it overlapped with IC, so I don't know if I will be able to go. But then we're going back to Purdue University in May 2022, and our go-kart is in the process right now as I speak. So we're trying to push to get ready. This year we didn't do as well as we wanted to do. But the next year, I told the other universities, watch out for us. We're going to come here and we're going to rock.
Well, good luck.
Thank you.
Awesome. Thanks, everybody. Thanks, Jack. Have a great afternoon, everyone, and we will see you next time.
Everybody wave.
Bye.
See you guys.